Every time you tap your phone or buy something online, maybe stream your favorite show, you're actually interacting with this hidden powerhouse, right? A database.
Absolutely.
These systems are doing incredibly complex things, crunching just vast amounts of information, like in fractions of a second. They're kind of the silent heroes of our digital world.
Yeah.
But even heroes, well, they face challenges. Today, we're going to dive into one of the most fundamental, but also notoriously tricky operations right at the core of these systems. It's called the join query.
Mm-hmm.
And it's absolutely vital for everything from, say, sophisticated data analytics to the machine learning models that power our recommendations. The big problem, traditionally, these queries can just slow right down when you're dealing with truly massive data sets, especially if they have to generate these enormous intermediate results along the way, even if the final answer you actually want is quite small.
Right. It's like that intermediate step blows up.
Exactly. Like sifting through an entire library just to find one single paragraph. It feels inefficient. So this is where a really clever idea called an output-sensitive algorithm comes in.
Yeah.
What does that mean? Well, it means the algorithm's running time isn't just about the massive size of all the input data it has to chew through, but critically, it's efficient based on the actual, often much smaller, size of the answer it produces.
Which makes a huge difference.
That's a potential game changer for speed, right? So our mission today is to unpack a recent, pretty groundbreaking paper. It looks like it delivers a significant leap forward in making these fundamental database join queries dramatically faster and also much more practically efficient. We're going to explore its ingenious techniques, its, surprising performance, and the real-world implications for how we all interact with data, maybe without even realizing it. Okay, so let's unpack this a bit. When we talk about join queries, maybe for those of us who aren't, deep into database architecture every day, what are we really talking about, and why are they such a cornerstone of today's data-driven world?
Yeah, good question. So imagine you've got like a spreadsheet with customer names and maybe another one with their order IDs.
Okay.
A join query is basically how a database intelligently links those two pieces of information together. So you can see, okay, this customer placed that order.
Gotcha. Connecting the dots.
Exactly. Connecting the dots across different tables or data sets. It's truly the workhorse behind almost any complex data task you can think of. Powering analytics dashboards, feeding machine learning models, or even just showing you all the details of your latest online purchase in one place. But the challenge, like you said, has always been performance, speeding these things up. I mean, decades of research have gone into this. And for certain types of these queries, specifically what we call acyclic conjunctive queries, you can kind of think of these as queries looking for simple patterns like chains or tree structures in your data. Nothing loopy.
Okay, acyclic meaning no cycles, no loops.
Right. For those, one of the most elegant and well-known theoretical frameworks was actually proposed way back in 1981 by Mihalis Yannakakis.
Wow, 81, that's foundational.
It really is. His algorithm had this runtime guarantee that, well, it essentially scaled with the size of your entire database. Let's just call that size D plus D, multiplied by the size of your final output. Let's call that OUT.
So OD plus DOUT. The bigger the input D and the bigger the answer OUT, the longer it took. Makes sense.
Exactly. That D times OUT term could become a real bottleneck if your output was large, even if it wasn't that large compared to the whole database.
So Yannakakis kind of set that theoretical benchmark. But I mean, in the decades since, surely there have been other big attempts to push those boundaries, maybe using completely different kinds of math.
Oh, absolutely. People have definitely tried. For instance, there was some really elegant work by Hue Eku and colleagues a few years back. They explored using these highly specialized techniques, specifically something called fast matrix multiplication, to get theoretical improvements.
Ah, matrix multiplication, like the stuff used in graphics and scientific computing.
Kind of, yeah, but applied to database joins in a very clever theoretical way. They actually managed to reduce that D multiplied by OUT term. So instead of D times OUT, it scaled a bit better, maybe like D times OUT raised to the power of, say, 5/6.
So slightly better scaling with the output size.
Exactly. Mathematically, it was quite impressive. It showed the power of these algebraic methods. However, and this is a big however for practical use, their approach had a couple of key limitations. First, it was non-combinatorial.
Yeah.
Meaning it relied on these complex algebraic properties and matrix operations that are often, well, less efficient or just much harder to actually implement and optimize within existing real-world database systems. They're not how databases usually work internally.
Okay, so Theoretically nice, but practically tricky.
Pretty much. And second, it didn't easily support common database operations that people really need, like aggregations.
Aggregations like summing things up, counting.
Exactly. Things like summing up total sales or counting unique visitors or finding the average value. These are crucial for analytics, and the matrix multiplication approach didn't naturally handle them well alongside the join.
Right. So the big question of achieving, practical combinatorial improvements, something that works well within current systems and handles things like aggregation, that question remained wide open.
It did, yeah. How do we improve on Yanikakis in a way that's actually usable day to day?
And this is where today's groundbreaking research really enters the picture. We've got this new paper by Shaleen Deep, Hangdong Zhao, Austen Fan, and Paris Koutris. And they're shaking things up, claiming a novel output-sensitive algorithm that improves on Yanikakis without those practical limitations. So what does this actually mean for, how databases might operate in the future?
Well, this paper, it really does present a significant advancement. They've developed a new combinatorial algorithm. That's the key part that generalizes Yanikakis.
Combinatorial meaning it uses more standard, logic-based database operations, step-by-step stuff.
Precisely. It's built on logical operations, comparisons, lookups, things databases are already good at. It avoids those complex algebraic structures. And because of that, it's inherently more practical and potentially much more efficient for real-world systems. What they show is that it's possible to evaluate these acyclic conjunctive queries, the same class Yanikakis looked at in a time that scales roughly like d plus OUT plus d times OUT raised to the power of 1 epsilon.
Okay, 1 epsilon. So that epsilon's doing some work there.
It really is. That 1 epsilon exponent might look a bit mathy, but the epsilon here is crucial. It's a positive number, and it depends on the specific query you're running. It might be something like, 12 or 13 or 1k for some k.
So it effectively shrinks that exponent on the OUT term, making the impact of the output size smaller.
Exactly. The larger this epsilon is for your particular query, the more significant the speedup becomes, especially as the output size OUT grows. And on truly massive data sets, this can be the difference between a query taking potentially days to complete, or maybe just timing out entirely, and finishing in, say, minutes or even seconds.
Yeah.
It's a fundamental shift, potentially, in what becomes computationally feasible for certain complex analyses.
Now, here's something I found particularly fascinating about this new paper, and honestly a bit counterintuitive. They seem to suggest that for some common query types, this new combinatorial approach can actually outperform those prior results that used fancy algebraic stuff like fast matrix multiplication.
Yeah.
How does that even work? You'd think the super specialized matrix math would always have an edge, at least theoretically.
That is remarkable, isn't it? And I think it highlights a really profound insight here. Sometimes these fundamental combinatorial approaches, the ones that are maybe more direct, perhaps simpler conceptually, easier to implement, they can actually be more powerful in practice than even the most advanced, highly complex algebraic techniques.
Huh. So clever structure beats complex math sometimes.
It seems so, at least in this context. It's really a testament to the power of, clever structural thinking about the problem itself. This new algorithm gives a provable improvement over the classic Yanikakis algorithm using combinatorial means and demonstrates that elegant, direct methods can still yield these incredible gains.
Okay, so how do they actually do it? What's the secret sauce behind this faster, more practical performance? Is it some completely new way of thinking about joins?
Well, at the heart of their approach is this really novel idea of carefully partitioning the input and evaluating queries in a specific order. They build upon the core ideas of the original Yanikakis algorithm, which itself is quite clever, but they introduce this recursive method. And this method intelligently splits the data based on what they call degree thresholds.
Degree thresholds.
Yeah.
Like how connected things are.
Exactly. Think of it maybe like you're a very clever event organizer for a massive party, right? And you're trying to find specific connections between people who knows who.
Okay, I'm with you. Big party, lots of connections.
Instead of just letting everyone mingle randomly and hoping the right connections emerge, which could be totally overwhelming and chaotic.
Yeah, takes forever.
You might strategically sort the partygoers first. You could identify the, let's say, heavy connectors, the really popular people with tons of friends and connections, and separate them from the light connectors, those with maybe fewer friends.
Right, the social butterflies versus the wallflowers, sort of.
Sort of, yeah. And then you process their potential connections separately and maybe much more efficiently because you've broken the problem down. You avoid that huge traffic jam of information processing all at once.
Okay, so it's about being really strategic about which parts of the data you process together and maybe when you process them. It sounds like a sophisticated way to avoid information overload inside the database itself, cutting down on unnecessary work.
That's precisely it. Let's take a slightly more concrete, simplified example. Say you have a path query where you're looking for a chain of connections. By 1 connects to by 2, which connects to by 3.
Like A knows B knows C.
Exactly. Instead of just directly joining all the data related to by 1, by 2, and by 3 together at once, which might create a huge intermediate result if, say, by 2 connects to tons of things, they might partition one of the relationships, say the connection between by 1 and by 2, which we might call Rx1 by 2. They could split this into 2 parts. One part for the heavy by 2 values, those by 2s that are connected to many by 1s, and another part for the light by 2 values. Then they evaluate the rest of the query, connecting to by 3, on these partition parts, perhaps using different strategies for the heavy and light parts, and then they combine the results at the end. This clever partitioning strategy allows them to avoid actually materializing those potentially huge intermediate results involving all connections through by 2 at once, and that's often a major source of slowdown in traditional methods.
And that degree threshold you mentioned is what decides who's heavy and who's light.
Yes, absolutely key. Choosing that threshold correctly is vital for making the partitioning effective. And, figuring out the best way to partition isn't trivial. So they use this other clever technique they call a doubling trick.
A doubling trick.
Yeah, it essentially lets them efficiently search for and find a really good threshold for doing this partitioning, even if they don't know the final output size OUT in advance. Which is important, because usually you don't.
Right, you run the query to find the output size.
Exactly. So this doubling trick helps ensure the algorithm kind of automatically adapts itself for maximum efficiency based on the data structure. And just to help characterize this improved running time and understand the epsilon better, they also introduced this new, simpler measure. They call it projection width, or PWQ.
Projection width.
Yeah, it sounds a bit technical, but intuitively, it's related to the structure of your query. It's essentially the maximum number of tables involved in the most complex sort of connected piece of your query pattern.
Okay.
And this PWQ value, this projection width, it directly correlates with that epsilon in their runtime guarantee, 1 epsilon. So it becomes a very useful diagnostic tool. You can look at your query, figure out its projection width, and get a good idea of how much faster this new algorithm might be compared to Yanakaki's.
Ah. Okay, so it gives you a predictor for the speed up?
Pretty much, yeah. It connects the query structure directly to the performance gain.
So let's bring this down to earth a bit. What does this actually mean for you, the listener, who might be interacting with databases every day, maybe indirectly? What kinds of queries, what real-world scenarios are likely to see the biggest benefit from this kind of advancement?
Right, the practical side. Well, this generalized algorithm, it significantly impacts several types of queries that are actually used very widely. It brings potentially really tangible speedups. For example, first path queries, we touched on these, like finding a chain pk by 1, xk plus 1, where you're following a sequence of take connections or steps in a network.
Like tracing a user's clicks through a website, or maybe analyzing a multi-step supply chain.
Exactly, those kinds of things. Analyzing dependencies, flows, sequences. For these path queries, their algorithm achieves a runtime that scales much better with the output size, specifically with that exponent being like 1k, a significant improvement. And what's even more impressive, they show an even further improvement just for path queries, getting the exponent down to 1 ceiling plus 1 2.
Okay, that's getting specific, but the point is, it's even better for paths.
Right, and get this, for K3 paths, like A connects to B, connects to C, connects to D, this improved result actually matches the known theoretical lower bound for combinatorial algorithms.
Oh, lower bound meaning you literally can't do any better.
Exactly. You cannot get any faster for K3 paths using this kind of combinatorial approach. It's provably optimal in that sense, which is pretty amazing.
That is amazing. Okay, so path queries get a big boost. What else?
Then there are star queries. These are also incredibly common, especially in hierarchical data structures. Think about finding all the components connected to some central hub.
Like a product and all its different features or parts.
Yeah.
Or maybe a manager and all their direct reports in an organization chart.
Perfect examples. For a star query, say Q with all male branches coming out from the center, the algorithm provides a similar substantial speed up, again, improving that exponent related to the output size, making it all in 1L. And what's neat here is that this result not only recovers some previous state-of-the-art bounds that were known for star queries using combinatorial methods, but it actually provides an alternative, arguably more elegant proof for them. And it also highlights that the original Yanakaki's algorithm itself, when analyzed using their new techniques, can also achieve this improved bound for star queries. It shows the inherent power was there, just needed this new perspective.
Okay, so these aren't just, obscure academic query types cooked up in a lab. Path queries, star queries, these are genuinely the backbone of countless real-world data interactions. We're talking social network analysis, biological pathways, fraud detection, supply chain management.
Absolutely. Countless applications.
So we really are talking about tangible speed-ups for everyday, important database operations. That's incredibly impactful for businesses, for researchers, for anyone dealing with large data sets.
And the impact, it actually extends beyond just finding the matching records, the tuples themselves. The algorithm is designed to be, as they say, easily extensible to support things like functional aggregate queries or FAQs and operations over structures called commutative semirings.
Okay, FAQs, semirings.
Right.
What does that mean in plain English?
Right. Basically, it means the algorithm can efficiently handle not just finding the matching data points, but also performing more complex analytical operations over that joined data. Things like counting the number of occurrences, summing up values associated with the matches, finding minimum or maximum values across the join results.
So not just find all customers who bought products A and B, but maybe find the total amount spent by customers who bought A and B, or find the earliest order date among those customers.
Exactly, those kinds of aggregations. Imagine calculating the average purchase value for customers who bought a certain combination of products, or tracking the minimum inventory level across a complex, multi-stage supply chain represented by joins. These are the powerful aggregate calculations that this algorithm can now handle with potentially much greater speed.
That adds a whole other layer of practical utility.
It does, and they've also shown how to handle self-joins. That's where a table is joined with itself, which sounds weird but is actually common.
Like finding pairs of friends in a social network, or maybe employees who report to the same manager.
Precisely. Analyzing friend-to-friend relationships, finding colleagues with shared attributes, things like that often involve self-joins. They show you can handle these through a pretty straightforward pre-processing step, meaning the core algorithm still applies.
So it really covers a huge range of common real-world database scenarios. Broad applicability.
Yeah, they've thought carefully about making it widely usable.
This raises, though, an important question, maybe a deeper one. How do we actually know these algorithms are truly optimal or close to it? You mentioned the K3 path case hits a lower bound, but generally, are there theoretical limits? Could someone come along next year with another trick and shave off even more time?
That's a fantastic question, and it gets into the realm of theoretical computer science and complexity theory. That's where the concept of lower bounds comes in. The paper doesn't just present the algorithm, it also provides rigorous theoretical lower bounds. These are mathematical proofs that essentially say, under certain widely believed assumptions about computational hardness, no algorithm of a particular type, like a combinatorial one, can possibly solve this problem faster than this specific time complexity.
So it's like setting a speed limit based on fundamental principles.
Exactly. It's defining the boundary of what's likely possible. Often these lower bounds are linked to deep, challenging questions in computer science, like the hardness of the Boolean k-click conjecture.
Okay, k-click. That's about finding groups of k things that are all connected to each other in a network, right? Which is known to be hard.
Right. It's a notoriously hard problem, believed not to have a truly efficient solution. By showing that solving certain join queries faster than their algorithm would imply an unexpectedly fast algorithm for k-click, they provide strong evidence that their algorithm is close to optimal.
So they're essentially saying, look, our algorithm runs this fast, and if you could do significantly better using similar techniques, you'd probably also break this other really hard problem that almost everyone believes is unbreakable.
That's the essence of it, yeah. It proves the tightness of their results for certain classes of queries. It demonstrates they've likely pushed the boundaries about as far as is combinatorially possible in many important cases. It's not just faster, it's likely near optimally faster within this class of algorithms.
Wow. Okay, our deep dive today has really shown how how innovative algorithms are constantly pushing the boundaries of what's possible inside these database systems we rely on. This generalization of the classic Yanikakis algorithm by Koutris and his colleagues, it really offers a powerful, practical, and importantly, combinatorial solution. It speeds up fundamental data operations and, surprisingly, often outperforms even those more complex non-combinatorial methods like the ones using fast matrix multiplication. That seems like a huge win for practical efficiency, for actually getting stuff done faster in the real world.
It really is, and it leads to, I think, an important question for you, the listener, to maybe consider. As algorithms like this one become increasingly efficient, how might our whole approach to designing and interacting with large-scale data systems evolve? I mean, what new analytical possibilities might suddenly be unlocked when we can process these vast, complex queries with really unprecedented speed? It could really push the boundaries of what we think of as computationally feasible and maybe transform what we can actually learn from all the data we're collecting.
That's a great point. What new questions can we ask when the answers come back in seconds instead of days? Fascinating stuff. Well, we hope this deep dive has given you some perhaps surprising facts and certainly some new insights into the really fascinating world of database query optimization. It's more dynamic than many people realize. Join us next time for another deep dive, where we'll explore more knowledge you need to be well informed.